Okay, Assalamualaikum and a very good morning. Okay, this week we are going to discuss on another types of antenna, which is the antenna arrays. This type of antenna is broadly used in communication system, and it is basically a multiplication of more than one antenna element, as shown in the figure. So what is antenna array? So it is basically a set of multiple connected antennas which work together as a single antenna to transmit or receive radio waves, right? So it begins with a single structure. This is called single element, and then the more than one elements are combined, okay, in series or in parallel to each other, okay, depending on the targeted frequencies, directivity, gain, and etc. Right, so once these elements combine together, so now it's formed a new antenna, and now it becomes a single antenna array, which consists multiple of elements. All right, so sample or example of array antenna applications are in satellite communication, wireless communication, military radar, and astronomical study. Okay, and in most cases the elements are identical, but it is not necessary. Okay, so for example, if we use simple microstrip patch, we can have the second element also in microstrip patch, and it can also be a different patch, and then secular patch, for example, and then the elements repeated again and again up to the targeted antenna performance. All right, for an array, it is assumed that the elements are identical, usually identical, have the same spatial orientation, excited with equal magnitude and phase, and no mutual couplings between elements, and the array property of an isotropic radiator. So meaning that all elements are excited and expected to radiate isotropically. Okay, so why antenna array is needed? Why don't we just use single element antenna design? Okay, for long distance communication, we need an antenna with high directivity. Okay, one example of high directivity antenna is horn antenna. Okay, that's usually having a bigger aperture size, right? However, single element antenna usually having wide radiation pattern but low in directivity and gain. For example, if we have a microstrip patch antenna, it's directive, okay, but it is a bit the beamwidth a bit wide. But for long distance communication, we require a highly directive, so that we require the beamwidth a bit smaller, so that the signal will be traveling at far distance if compared to this one. All right, we can achieve narrow beamwidth and higher directivity by increasing the aperture size, for example, the horn antenna. So we can control the width and the length of the aperture to increase the directivity. However, this may result in very large structure, and it's difficult and expensive to fabricate. Therefore, there's antenna array comes into place where we can use smaller size of structure, single element, and the same size will be repeated together. Okay, and then it becomes an antenna or an array, so that we can have the size of the element is maintained, okay, but we enlarge the electrical dimension of the design, and then so that we can improve the directivity. Okay, so the size of the single element is more or less the same, but we increase by having the array configuration, we can have larger electrical dimension of the structure, so that we can have a higher directivity of the antenna. And the advantages and disadvantages of the array antennas are as shown. So we can increase the signal strength, higher directivity, minor loops, okay, minor loops, side loops and back loops, and then high signal to noise ratio, high gain as well. Okay, power wastage is reduced because most of the power will be channel or will be directed to the intended direction, so that we can have better performance in overall transmission. While there's the disadvantages of this array antenna is resistive losses may be increased, and it's quite difficult to mount and maintain, and huge external space is required to place or to mount the antenna. Okay, antenna array radiation pattern. So each of the radiator, okay, for example, if you have a single dipole λ/2 dipole antenna, okay, each direct radiator or a single element structure will produce its own induction field. So when in array structure, the elements are placed so close so that the induction produced by one element will be in close contact with the adjacent elements. All right. Therefore, the total field or radiation produced by multiple element structure or an array will be the vector sum of the individual induction or radiation produced by single elements. Alright, so this happened when the fields from the elements interfere constructively, so it's added up in magnitude towards the intended direction, while destructively or cancel in other directions. Alright, so for example, if we have a single element dipole antenna, usually the radiation pattern will look something like figure 8. So this is single element. So, and if you compare to the two element radiation pattern, so now there's two elements, element 1 and element 2. Right, so now the radiation pattern looks a bit more directive. Okay, so the beam width also becomes narrower if compared to single element. So this one only one element. And compared to three elements, so it's become narrower and a bit more directive. And when you increase the elements further, so it becomes more directive, and the beam width also becomes narrow if compared to lesser elements. So we can control the overall pattern by controlling the geometrical configuration of the array, and then the relative displacement between elements, okay, the distance between elements, the excitation in terms of the amplitude, and also the phase of excitation. Okay, this is the fundamental of array. So if you have more than one element, so antenna 1 up to antenna n, Okay, so the field produced or radiation produced by the first element, the first antenna, given by E1 equal to E1, the magnitude of the fields from antenna 1 multiplied with the factor or the phase. Alright, so and this from E2 up to En. Same goes to the current. So the total field for this array and array structure is given by the vector sum of individual elements in the array. So E1 plus E2 up to En. And the psi here is given as KD cos theta plus beta. So K is the wave number, K equal to 2 pi over lambda. D is the distance, separation distance between each element, and beta is the phase difference, excitation phase difference between the element. Okay, next is the array factor. So this is one of the important parameter in designing array antenna. So array factor is a function of number of elements, geometrical arrangement, relative magnitude and phases, and spacing between elements. So the array factor is given by this equation, and the normalized to the number of element array factor is given by this equation. Again, K is the wave number equal to 2 pi over lambda, and D is the separation distance between element. For example, in this figure we have two elements or two infinitesimal dipole oriented along the z-axis. So this is the structure 2 and this is the element 1, and separated by D. Okay, and beta is the phase difference, excitation difference between the element. So beta is somewhere here. So here is the origin at the center, okay, between the elements, and usually origin. Alright, and array factor will be much simpler if all elements having identical amplitude, phase and spacing, and it does not depend on directional characteristic of the radiating element. And the total field radiated by an array that consists of multiple elements is actually a product of the field of single element at selected reference point multiplied by the array factor. So the total field equal to the E produced by single element, providing that all elements are excited by the same isotropic source multiplied by the array factor. So the selected reference point, for example, in this case is P, so it is one point at the far field zone. Okay, let's use two element array as an example. So assuming that we have two infinitesimal dipoles positioned along the z-axis, so we have here 1 and 2 separated by d distance, and we are assuming that there's no coupling between the elements. So the parameters involved, we have the polar angle, and then we have the distance between the elements, and then for phase variation we need to consider the polar angle, while for the amplitudes we just need to consider the dr and the theta on its own. And the total fields radiated by this two element array is given by the vector sum of individual elements E1 and E2. In this case, we have, for example, the first element and the second element, and it is given by this equation. So this is the intrinsic impedance, okay, and K is the wave number, I naught L the length of the antenna, multiplied by this complex function. Okay, again, beta is the excitation phase difference between the elements. Okay, so the total field equation from previous slide may be reduced to this equation. Okay, can be simplified further, and the final total fields radiated by an array can be calculated by this equation, in which it is the single element, the field produced by single element multiplied by the array factor, and the array factor is given by this equation, and they normalize to the number of element. Array factor is given by this equation. So in the far field zone, we assume that the two element is uniform, and it is excited by an isotropic source. So we are assuming that the elements also identical to each other. So we can use this basic equation, the total field again equal to the element factor or the single element field multiplied by the array factor. Okay, let's look at an example. Find the progressive phase shift beta so that the main beam is steered to theta equal to 60 degrees. So we have the radiation pattern. So here is 0. So 60 degree is somewhere here. Okay, so the main beam steered to 60 degrees. So the main beam steered to 60 degrees. So given that D equal to lambda over 2, the separation distance between the element. Right, so we can calculate the beta here. Okay, by using this AF equation. Alright, let's write the equation first. So AF equal to 2 cos 1 over 2 KD cos theta, theta given by 60 degree plus beta. So how to find beta if you don't know what is the AF? So since the main beam is given, so the main beam meaning that this is the maximum radiation achieved by the design, so the AF will be equal to 1. If it is the minimum, so AF equal max equal to 1, so AF min or null equal to 0. So in this case, what is K? So K is the wave number equal to 2 pi over lambda, and then D given as lambda over 2. So again, so AF equal to 1 equal to 2 cos 1 over 2. Your K is 2 pi over lambda multiplied by lambda over 2 cos 60 degree plus beta. So from here you can calculate your beta. So beta equal to negative pi over 2. Okay, let's look at another example. Find the nulls of the total field when D, the separation distance between the element, is lambda over 4 and the phase excitation difference equal to 3 values. So A when beta equal to 0, B when beta equal to pi over 2, and C when beta equal to minus pi over 2. Okay, so to get the nulls or the maximum radiation, we need to use the total field equations, so which is basically the multiplication of the single element multiplied with the array factor, or it can be simplified by this equation C representing the fields for single elements multiplied by the so this is the single element component, while the array factor component is from here, from cos until this point. So this is the array factor. So in so the nulls, for example, you have the radiation pattern. So this is the main beam, okay, the main beam direction, and these two are the nulls point where the fields is 0. Okay, so you need to perform 2 steps calculation. The first one, you need to consider the fields of the single element. Secondly, you need to check the array factor. Okay, so to get this one, so first you have this C cos theta equal to, so the field when it is null, the total field will be 0. So the first step. So the second step, the array factor cos 1 over 2 kd cos theta plus beta equal to 0. So you need to determine the theta or the theta n. So we assume theta equal to theta n, so in which the nulls appear. Okay, so you need to determine what is the theta. Okay, so for d equal to lambda over 4, so beta equal to 0 in this case. So this is the equation. So you need to find what is the kd just now. So k equal to 2 pi over lambda, and d is given as lambda over 4. Okay, so in this case beta is 0. So first step is to get the field for single element. So since for null, so we need to determine the nulls. So for nulls, the fields at nulls equal to 0. So therefore theta n equal to inverse cos, so it is equal to pi over 2. Okay, so for single element radiation pattern, the nulls appear at pi over 2. So how the figure looks like. So this is the radiation pattern at 90 degree. Okay, the nulls appear. Okay, the second step is to get from array factor. So cos kd cos 1 over 2 kd cos theta plus beta. So beta equal to 0. So kd, k from here multiplied with d lambda over 4. So equal to 0. And when inverse cosine of 0, you may get different values. Plus minus of pi over 2, 3 pi over 2, and etc. So now try to get what is the theta values. So in this case, when you inverse cos of those values, so you get error. It doesn't exist. So from these two, only one nulls occurred at 90 degree or pi over 2. Okay, so from the second step, so this is the first step, and from the second step, okay, from the first step you plot the element radiation pattern. From the second step, so this is from the first step. From the second step, you plot the factor, so AF. radiation pattern. So how the pattern looks like, so it doesn't exist, meaning that it's maximum in all direction. Okay, it's maximum in all direction. Okay, so next what I need to do is to get the total fields radiated by this array is by multiplying. Okay, remember the E total is equal to E of single element. I put it as S multiplied with the array factor. Okay, so you need to multiply the elements with the array factor plot. So multiply them. Okay, we'll see the area with 0 fields will be multiplied with the one that having magnitude. So the final fields we got as figure 8. Okay, next for B, again you need to find the nulls. Right, so when D separated, the elements separated by lambda over 4, but now the phase difference between the elements given as pi over 2. Okay, the earlier one in part A, it is beta equal to 0. So the same steps, so you need to consider the element and also the array factor. So the first step, the element is cos theta, again for nulls equal to 0. So theta again appears at pi over 2. So for element, the nulls appear at pi over 2. Okay, once you've plot the element radiation pattern, now the second step, consider the array factor. So in this case, you already have the beta. So beta equal to pi over 2. So this is basically the simplification of the equation. Alright, in which the cos 1 over 2 kd cos theta plus beta. So k to pi over lambda. So it's cos 1 over 2 2 pi over lambda multiplied by d is lambda over 4 cos theta plus pi over 2. Okay, so when you simplify the equation, now you got lambda over 4 and here also lambda over 4. Okay, so again for nulls it is equal to 0. So it appears when theta n equal to 0. Okay, so theta n equal to 0. When you try, when the angle or the theta equal to pi plus minus pi over 2, it doesn't exist. And another one, 3 pi over 2 plus minus, also it doesn't exist. So for this particular case, the nulls appeared at 90 degree and also 0 degree. Okay, so for the second step just now, the nulls appear at theta equal to 0. So for array factor, the second case, the second step, so the nulls appear at 0. Okay, alright, so next step is to multiply them, okay, because E total equal to E single element multiplied with the factor. Okay, so you multiply them. So in this case, it's 0 crossing at this one until here, something like this. Okay, so you multiply them. So you will get some shape here. And then here. And also at the bottom. Okay. So this is the final fill in which the nulls appear at 90 degree at this point and also at 0 at this point. Okay, for part C, the same steps. Again, you need to consider the element and then plot the element. For the element, it appears at pi over 2. Okay, appears at pi over 2. And then for the factor, it appears at 180 degree. Okay, so at 180 degree for array factor, and then multiply them. So finally you get for this particular case, so the theta n or the nulls appear at 90 degree and 180 degree. So again at 90 degree and also at 180 degree. Okay, so previously we have seen for 2 elements array. So now if you have more than 2 elements, up to n array elements, so the geometry or the configuration looks something like this. Okay, for example, the first element, second element separated by distance d, and then the phase excitation difference between each element given by beta. So the array factor of n array elements may be simplified to in exponential form as e to the power of j n minus 1. So n is number of element, and the psi factor given by kd cos theta plus p. Okay, so the normalized array factor may also be calculated by the exponential function of this. Okay, normalized to the number of element, and also this equation may be used to determine the array factor of the array elements. Okay, for an array element, so the maximum beam or the main beam occur when the psi equal to 0, and the other main maxima or other second main loop may be determined for the m factor of 1, 2, 3 and so on. Okay, because for a radiation pattern in 2D, it looks something like this with side loop, for example, something like this. Okay, so this is the main beam. Okay, the main beam in Cartesian appears something like this, and followed by the second maximum there. Okay, here is null, so here's the first null. Oops. Okay, same goes to the left hand side, so this is the second maximum and so on. Okay, so this is for the mean maxima, and for the nulls we can determine at which angle. Okay, the nulls is occurred, right? So it can be determined by finding the theta n given by inverse cos of this equation. Okay, so in previous example we have seen the radiation pattern when the two elements of antennas is separated by distance d equal to lambda over 4. Now we are going to look at what happened to the radiation pattern when the d is increased from lambda over 2 up to 2 lambda. Alright, so again, we are still considering 2 point source or 2 elements of array antenna. So the E field is the total E is basically the vector sum of E1 and E2. and we can determine the maximum beam and also the minimum or null beam location at which theta. Right, so the same step as earlier. So for when the separation is lambda over 2, so maximum beam occurred at theta equal to 90 degree, 0, 90, and also 270. And the nulls appeared at 0 degree and also 180 degree. Right, so this is when d equal to lambda over 2. So the maximum appeared at 90 degree and 270 degree, and the nulls appeared at 0 and 180. So this is when you considered 360 degree pattern or angle. And for half power beam width, right, we consider at negative 3 dB or at half of the maximum power. So this is the point of half power beam width. So we can determine the angle once we know the angle of the pattern. Okay, this is what happened when the distance between elements is increased to lambda and also to lambda. We can see that the maximum beam appeared at a different angle as well when d equal to lambda. So 4 nulls and 4 main beam appeared within the radiation pattern, while when d equals to 2 lambda, more main beam we can see at 0 and 180 degree, while the minor lobe or the other maximum beam also occurred at these angles. So from here we can see that the theta, the radiation or directivity of the array antenna can be controlled by controlling the geometry or the distance between elements, and also the theta, the angle theta or beta of the phase difference between the elements. Okay, as mentioned earlier, we can represent the radiation pattern either in polar plot or in Cartesian plot. For example, here the maximum beam occurred at this point. So at theta equal to roughly around 30 degree. So the maximum beam appeared here at 30 degree, and then the null appeared in between the main beam to the next side lobe. So there's a null, and then followed by next beam, maybe around 70 degree, for example. Okay, and here, and depending on how many loops you have in the array system. Okay, let's look at another example. A 3-element array of isotropic stars has the phase and the magnitude relationship shown in the figure. So you have the first element, and then the second and the third, and these elements are separated by the distance d equal to lambda over 2. So find the array factor. So the array factor, so you can use the equation whether you use method 1 using the cosine function, or the second method using the sine function of psi. And next you need to find the null's location, right? So the answer at the bottom here is for the B. So the null's location appeared at 99 degree and also 146 degree. Okay, to solve the example, you can use method 1 or method 2, but in this sample solution, it used method 2, which use the sine function. So of the psi, so psi is equal to kd cos n plus cos theta n plus beta. Alright, so the array factor is given by this equation. Okay, if the theta is known, so you can determine the overall AF for a reflector. And the second question asking about the null position. So null position appeared by you can calculate that by using this equation, inverse cos of lambda over 2 pi d. So d in this case is lambda over 2, and negative beta plus minus 2n divided by the number of elements. So in this case, we can get the first null appeared at 99 degree and the second one appeared at 146 degree. Okay, it is the end of the first part of array antenna. We are going to continue on the second part of array antenna. Thank you.